Alright guys, welcome back to a new video. So in today's video, I'm going to be showing you guys what unsupervised learning is, how it works, and how we can implement it using Python. So first of all, what is unsupervised learning? So in AI, we have different subsections. We have machine learning, and inside of machine learning, we have neural networks. But machine learning is split into two different parts. We have supervised learning and unsupervised learning. Now, supervised learning is any type of learning that uses labels. So when we're training the model, we give it labels and we basically tell it, for example, let's say we have a model that's trying to differentiate cats and dogs. We tell it images of cats and images of dogs. So then it can learn different patterns between these images. Now with unsupervised learning, we don't have any labels of our images. We have a bunch of images, but our model is going to group these different images without us telling us the different groups. Or us telling the model the different groups. So now I'm going to go to a whiteboard and show you guys how this works and how our model does.
All right, so how does this process actually work? So let's go back to the example of dogs and cats. So how are we going to differentiate them using unsupervised learning? So before that, let's just recap what I just explained. So we have AI, and a subsection of AI is ML. ML has supervised learning and unsupervised, so we can say US. So and then we also have neural networks. But today we're just going to be focusing on our unsupervised learning. So we know that supervised learning needs labels. So unsupervised learning, it has no label. So we just give it a bunch of data, in this case a bunch of images, and the model is supposed to figure out the parameters without us telling the model which is which. So for example, let's say that we're just going to have a two-dimensional model. So basically like two different characteristics for dogs and cats. Now, because we have a dogs and cats model, it's not going to be accurate. It's not going to be accurate at all because the differences between dogs and cats, it can't just be noted in two different parameters, right? So that's why you're going to have more dimensions or more parameters in a model like that. But in this case, I'm just going to show a 2D example because obviously I can't draw out a bigger dimension other than 3D. So, alright, so instead of dogs and cats right now, we're just going to be focusing on leaves. So we're going to be talking about, there's going to be two different types of leaves. And basically in this made up example, a different type of leaf is going to be the stem size and the color, right? So that's going to determine our different leaves. So we're just going to say leaf 1, let's just call it uh, leaf 1, right? So let's say L1, and we have L2. All right, we have some type of graph, and we have some data. So first, for our y-axis, we can say that this is going to be the height of the stem, and for the x-axis, this is going to be the color. 1 is going to be maybe, let's say, white, and then 10 can be 10 can be black, and the more you go, the more darker the color gets. Let's just say, so we can say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, and for the height, we just have 1, 2, 3, 4, 5, 6, 7, 8. All right, so now what we want to do is let's plot the points out. So let's say for L1 we have some data. So maybe we have some data right here for L1. Like this, and L2 maybe some data right here, just like this. Now, this is a really concrete example. It's super easy just for our human eyes to basically kind of sort out this data into two groups, probably on this line. But for a computer with who can't understand it, it's just going to be just as hard as any other graph. So this process is going to be the same for any amount of groups, any amount of data, no matter how spread it is. I'll show you an example on the computer after I explain this. So basically, what we're going to be doing is this is one way to do unsupervised learning, and basically it's called k-means. So k is going to be how many groups that we have. So we already know we have two different types of leaves. So now that we know that we have two groups, what we're going to be doing is we're just going to be putting two different center points. Okay, so I'm going to use this marker, and these are going to be the center points. So first, what the model's going to do is it's going to put two different random center points randomly on this graph because it doesn't know anything. So we're just going to put one right here, and let's just say one right here. And this is random. So now what we're going to be doing is we're going to be finding the distance between every single node or data point to this, the distance between this to every single data point, and we're going to be basically grouping or whichever data is closest to this is going to turn into that type. So let's say that this is 1, this is going to be 2. So for example, this is closer, 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 right? So whichever pieces of data is closest to this is going to turn into this type of data. So basically, eventually we're going to have data that kind of looks like this. Right, I'm just trying to recreate this data. Maybe this is 1. And then we'll turn the rest of them into 2s. I'm just drawing it out. Right, so we kind of separated the data. And the data points don't change, obviously. It's just they change groups. So now our number 2 center point is gonna go into the average. So it's gonna be right here. And our number 1 is gonna be somewhere right here. Right, this is gonna be, I'm just gonna shade it in so you know it's the center point. And the process continues. So it figures out whichever is closer. It's going to change all of those, and it's just going to shift the center to them. So maybe now, let's just say that we realize that this is closer. It might not be, but let's say that this is closer. As an example, this is going to change to that to 2, right? And then your center is going to change to. Center is going to go over here, and now maybe this center is going to change over here, and eventually we have a couple of different groups. Sorry, 1, 2, and eventually we have our groups like this. So it might be not like the clearest example here, but as long as you kind of get that the centroids are going to be placed randomly around this graph based on the amount of groups that you have. And what it's going to do is it's just going to take all the data nearest it, it's going to turn it into that type of centroid, and the centroid is just going to move. So if this isn't clear to you, I'm just going to show you a more visually appealing example on the computer. So maybe that'll help you understand this concept a little bit more quickly. All right, guys. So right now I'm just going to show you guys that k-means that I just explained, and I just want you guys to get a better understanding on basically how k-means works. So right here we just have some random data, basically what I showed you, but it's a little bit more visual appealing. We have 10 different sensors, and we just have pretty random data. You can see some of them are pretty clustered up, and it's hard to see. It's hard to see how many groups there are. Right, for example, maybe this is one group, or it might be 2 right here. Yeah, so our data is pretty random. And what our k-means is going to do is it's going to try to figure out how many groups there are and which of these are groups. So what it's going to do is we know that there's 10 different groups of data. So it's going to plot 10 different sensors over this map. And it's just going to do the process I just explained there. So it's going to check all the data closest to it, to the center, and it's just going to move the center based on that data. And just going to keep continuing this process As the center moves, it'll have a better understanding about its group, and eventually it'll get better and better, and it will have the perfect centers. So there's a couple ways to measure how good these centers are, and the one I'm going to be talking about today is going to be inertia. So what inertia does is it sees how far um, the data points are to the center, and it's going to be squaring that and summing all of those squares in each cluster, right? So, for example, let's say our centers are here, or the centers are on the map, and now they're fine tuned, so they're really in the different groups, and you're just going to be finding the distance between each center and each point. You're going to be adding that, squaring them, and basically the higher the inertia, the worse the score, because if the inertia is um, if the inertia is really high, well, that's going to mean that your centers aren't as close to the data as you wanted to. And basically, the more centers that you have, the better, the lower the inertia is going to be. Because if you'd only had two centers, then if the data is spread across the entire graph, some points are going to be really far from that center. But when you have three, they're going to be a little bit closer to each center. So that's basically how inertia works. This is a graph on the inertia of this graph. So there's basically 10 groups of data, and this inertia is going to tell us what the optimal amount of centers are. So basically, what this graph is telling us is the optimal amount of centers is about, I'm going to say either 8 or 9. And how you figure this out is whichever point does the data start to become more consistent. So, for example, we see how there's a big leap here, and then there's a smaller one, but then it gets smaller and smaller and smaller, and eventually around here, the data gets a little bit more consistent. And there's another method called the silhouette score. I'm not gonna get too deep on how that works, but that's just another way to understand how optimal our K is for our sensors. So it's just going to be running the inertia first, and then it's going to show us our silhouette score. And the silhouette score is just the highest point is what's it's going to be predicted. So it basically thinks that 8 is going to be the optimal value, and for inertia, it's about 8 or 9. So yeah, so it's pretty optimal. So if we check here, with our eyes, we can see that maybe we see that there's 1, 2, 3, 4, 5, 6, 7, 8, right? Maybe you can think of this as 9, so it could be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can see how the inertia and the silhouette score calculated, and basically showed us that our k means is doing pretty good. So we think it's 9, and our k means clustering is doing 9. So that's basically how k means clustering and how unsupervised learning kind of works, pretty simply explained. So now we're just going to use this knowledge of k means, and let's just create a project that's just going to compress images using unsupervised learning.
All right, guys. So now let's actually start coding our application that's going to use k-means clustering. So what we're going to be doing is we're just going to be creating an application that can compress images, and it's just going to block out all of the background noise, and because there's less background noise and less detail in the background that's not necessary, the image will be more compressed, right? And how it's going to be doing this using k-means clustering is every single color is going to be one cluster, and the less clusters there are, the less colors there are, and the less colors there are, the less background noise there is, right? So that's how our application is going to work. Now let's get into coding it. So first we need to import everything that we need. We're going to need matplotlib and scikit-learn. And if you wanted to download the images and compare the sizes, you can also use OpenCV, right? So matplotlib is just going to be useful to show the images, for example, like this. And scikit-learn is just what we're going to be able to use to actually do our k-means clustering. So we're not going to be doing k-means clustering from scratch today, but that's going to be for another video. All right, so first let's read our image, and right now I just have this picture of a rose. So for example, let's say that we want to pass this rose into a supervised learning model, right? We want to basically this image in particular has not a lot of background noise, but we want to even fine tune this image so it has less background noise, which can help our model learn better, right? So we can just read this image, and it has three parameters for the shape: 600 by 900 by 3. Let's make this two parameters, right? This is just going to make it easier for us to read it, right? And now we can actually do our k-means clustering. So we just want to say k-means equals k-means, and we want to set the clusters to any number that you think is going to be accurate enough so the image is useful, right? So you can actually recognize what the image is, whatever you think, but not too high so the compression doesn't really even help. And now we just want to use this k-means on our image, right, by k-means.fit on the image of x, right? And now we're just going to use the cluster centers, and we want to reshape our image, create an image with our image shape that we've created here, right? So we want to first get our clusters, and now we want to make the shape of that image into our original shape, right? Now we just want to show this image, and let's see how our compression has worked. Okay, so perfect. So we have an image. We can still tell that it's a rose, but you can see a lot of the background noise was cleared, and this can be a good image for testing. But let's say we want to just make it a little bit more clear. We might want to set the clusters to 6, right? And you can see it's running through the model, but now it's going to use 6 different centers, right? And as we talked about, the inertia is going to be less as the centers are more, right? And now when we show this, you can see the image is a little bit better. You can see we have the green petals, which is probably what we were looking for. And yeah, perfect. And we can even increase this even more so I can show you how that's going to look. All right, so now it's using 10 different sensors, right? And it's taking a little bit longer, probably because it has more clusters. And now we can show this image, and you can see it has a lot more detail to the image, especially over here. And this is a really good image to use, probably for our training data. Now we can download these images by clicking this button. But I already have the images downloaded, and I'll show you the compression results. All right, so the images that I downloaded were the before and after of the roses, right? So basically we have our before, which is just the image that I showed you right here. And this image is just going to be, the bytes of this image is, sorry about that. The bytes of this image is 131 kbs, and the after image with 2 clusters is going to be 78 kbs. So we almost cut the compression in half. We almost made our image half, the size of the image half as much, right? Which is really useful, especially when we have a lot of images, and images that have more background noise and have more detail. It's going to work even better. Like this image, there's the background noise was almost all gone, and even with that, we still have compression that is really really good. All right, so anyways, that's it for this video. Alright guys, thank you guys for watching this video. I hope you guys enjoyed. If you guys did, please make sure to hit the thumbs up button on the video. And if you have any questions about the video, you can just write them in the comments down below. All this code is just going to be on GitHub, so if you had any syntax errors or any trouble with the code, you can just look on GitHub and figure that out. But anyways, thank you guys for watching this video, and until next time,